Hello everyone, and welcome to this week's video lecture where we'll be looking at developing fraction operations part 2 based off of chapter 15 in John Van de Waals Teaching Elementary and Middle School Math. So last week we looked at adding and subtracting fractions, looking at conceptual models and leading into algorithms. And so this week we're going to continue on looking at multiplying and dividing fractions. Again, looking at different types of visuals and ways to build a conceptual understanding of those processes that lead into some efficient methods with algorithms, and that will be our goal for today. So reviewing from last video lecture, same basic principles apply. In order to make sense of these, here are some of the ideas that we try to aim for as teachers. Again, beginning with contextual story problems. Again, trying to not begin with abstract notions that we can't wrap our heads around, but something that we can picture and identify and think about and relate to. Use benchmark estimating. Again, the idea of thinking, is the answer going to be more than 1, less than 1, more than 2, less than 2, just to really think about the numbers involved. To explore using models and visuals. Again, trying to make sense visually of what's happening. And think about how those models connect to algorithms. And again, there's a lot of misconceptions when dealing with fractions, and so addressing them explicitly. And so, as last week, we'll be using these same principles again to guide through multiplication and division. So to begin, well, here's a question. When you think of the multiplication problem, 5 times 3/4, what does that mean to you? Can you draw something out for there? And what's the answer? Why does that make sense? Well, let's start there and begin unpacking fraction multiplication with a problem like that. Well, again, to begin to unpack that, we're going to start with some conceptual tasks, story problems, and estimation. And in the standards, when we think about starting with multiplying by fractions, it goes through a purposeful progression where we start with a whole number times a fraction because it's going to be more easily related to previous learning. For example, in the past, when we saw something like 4 times 3, we could visualize that in our head as realizing it's 4 groups of 3 and draw it out and think about the meaning of 4 times 3. Well, when multiplying a whole number times a fraction, it's really the same meaning, right? 5 times 3/4 would just mean 5 groups of 3/4. So if we can picture what 3/4 of something would look like, we have 5 of those, and that's what we're going to try and see how much we have all together. So let's start there, all right, with thinking about groups of meaning of multiplication. So here's a little scenario to start with that in mind. Let's suppose Mia filled 6 planters with 2/3 of a pound of soil each. How many total pounds of soil did she use? Well, again, so to start with this, we may begin with estimation questions, things like this. Do you think she used more than 6 pounds of soil or less than 6 pounds of soil? Well, again, if we understand the problem, we realize, well, she had 6 planters, each had less than a pound, so it must be less than 6 pounds. And even just questions like that help us stop and make sense of the situation to think through, and we could ask other questions as well. But can you stop right now and see, can you draw out a visual picture for this? Why don't you pause the video and see what you can draw out to get the answer visually for this problem. All right, well, let's take a look. Obviously, there are many ways to, to draw this out. There's not one right way to do that. But just over one example here, if we decide that, maybe we're going to use a rectangle that would represent, 1 pound of soil, always defining our whole, then we could think about it in terms of planters here, that in the first planter, I've used 2/3 of a pound, and in the second planter, I've used 2/3 of a pound, and we know that the story problem says that Mia has 6 of those planters. So just visually, one way to draw this out might have looked something like this. And we can kind of look at it visually here. And to think what this answer would be, well, we can start trying to make whole pounds of whole pounds of soil. So for example, we might visualize it this way. It takes 3 of them to make a pound, so maybe those 3 would be the first pound, and those 3 would be the second pound, and those 3 would be the third pound, and those would be the fourth pound, and so it should be 4 pounds of soil. So we see if we have 6 groups of 2/3, that the answer that makes sense would be 4 pounds of soil. And again, we start with visualizing and making sense of a groups of context. Was that similar to what you did? All right, well, let's look at Oops, let's look at the PowerPoint here again. Let me pull that back up. There we go. And let's go to take a look at what grade level are we talking about with this. The standard here at the bottom of this slide says this is a 4th grade standard. And as you can see there, it says solve word problems involving multiplication of a fraction by a whole number. And then it gives an example of a problem very similar to the one you just saw. So that's exactly where they're starting in 4th grade, making sense of that. Now, after we do a whole number times a fraction later, we'll look at the grade level in a second, a whole number times a fraction, we can look at and flip it around, a fraction times a whole number. So for example, let's change that problem just a bit. Suppose Mia had 6 planters, and she planted tomatoes in 2/3 of them. How many planters had tomatoes? So same numbers, but a different problem. Can you take a second and draw that out and see what that would look like if you drew a visual for this? All right, well, let's see what you did here, and we'll take a look at one possible way of looking at that here as well. So there was our last problem. Let's change it here. This time she had 6 planters. All right, I'm going to draw out 6 planters. And the goal is that she planted tomatoes in 2/3 of them. So really what we're looking for is we want 2/3 of the 6 planters. Well, one way to think of that is to, again, think about breaking these into thirds. So if we break it into 3 equal groups, we have 2 of those 3 equal groups. So it might look something like that, right? That's what 2/3 of 6 planters might look like. Again, we have 2 of 3 equal groups of those planters. And again, we still see the answer is 4, which it should be, since multiplication is commutative. But in this one, it would be 2/3 of 6 equals 4. And again, we could still say it's 2/3 groups of 6. The language gets a bit more awkward, but we're looking at 2/3 of 6, and we get the same answer either way. When we go back to the PowerPoint here, we can take a look and see that actually this is a 5th grade standard. So again, there's a progression through the grades that happens, doesn't happen all at once. But if you look at the standard on the bottom, that's what that standard is just saying. It says interpret the product a over b times q, that's a fraction times a whole number, as parts of a partition of q into b equal parts. Meaning, like we just saw, we took 6 into 3 equal parts and took 2 of them. So again, that's what we're looking at there in a 5th grade standard visually. Also in 5th grade, obviously here we begin multiplying a fraction times a fraction. And here's a friendly problem. We can make these messy or friendly, but here's a friendly one. And let's take a look. Let's suppose Devin had 3/4 of a pizza left in his fridge. He ate 2/3 of those leftovers for breakfast. How much of the original whole pizza did he eat for breakfast? Again, why don't you pause for a second and try and draw it out. What would that look like for you if you drew that out? All right, well, let's take a look at this. Again, this is a friendly problem, but that's a good place to start to try to make sense of some friendlier ones. It says that in the morning, I guess Devin came downstairs and there was some leftover pizza from last night's dinner. There's our whole pizza. And so there was 3/4. And Devin ate 2/3 of the 3/4 that was left over from the previous night. Well, this one's actually interesting. If we look at this, is really friendly because, well, there's 3 kind of sections left, and if he ate 2/3 of that, wouldn't he have just eaten 2 of those sections? Yeah, so Devin would have just eaten, 2 of those 3 sections. And so here we see that according to the question, it said how much of the whole pizza did he eat for breakfast? Well, he had half of the entire pizza. And again, we see that what that looks like in an equation is that we were looking at he had 2/3 of the 3/4 of a pizza. And we see that when we do that, the answer should be half, which we'll see it is. But again, we're just starting with making sense of a situation. 2/3 of 3/4 of a pizza will be the same as 1/2 of the whole pizza. Again, just starting with some visuals and making sense using some of the meanings here of going through. All right. And again, when you look at the grade level there, we see that this is a 5th grade standard of looking at fractions times fractions, starting visually here. Now again, so far we've done all area models, but again, we can use length models as well. And here's a situation that says on Monday, I ran 5/6 of a mile. Big workout for me, I know. And on Tuesday, I ran 1/2 of that distance. So, um, so less workout. I mean, how many miles did I run on Tuesday? Now again, you might start with those benchmark estimation questions. And even though it may seem obvious, it's not always. You might just ask students, so did Adam run more than a mile or less than a mile on Tuesday? It may seem obvious, but that's okay. We want to start with them actually stopping to think about the problem. Well, if you ran less than a mile on Monday and did half of that on Tuesday, if we make sense of that, he definitely ran less than a mile. And you might ask then, do you think he ran more than half a mile or less than half a mile? And even reason through that. And these are just good ways to start thinking about the problem before we start drawing it. So tell you what, can you pause for a second and again try a number line and see what would it look like on a number line to show what 1/2 of 5/6 of a mile would be. Okay, well let's take a look. So if we take a look at a number line, and let's just define our number line from 0 to 1 as 1 mile. And on Monday, I did 5/6. So I'm going to break the line into 6. 1, 2, 3, 4, 5, 6 sections there. And so this one here would be at 5/6. So that was my Monday workout. On Tuesday, I only ran half of that. So see, that's 1, 2, 3, 4, 5. So it doesn't break up evenly in 2 sections. So I can think about it different ways. But one way is if it doesn't break up evenly in sections, what I might do is partition this further, right? If I break all of these up a little further, each of those into half, now I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sections. So each of these, represents twelfths now going through. And now, just looking at it this way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's 10 twelfths to get to Monday's workout. So that's where, again, Monday, those are equivalent. Then half of that would be 1, 2, 3, 4, 5, or 5 twelfths. And so that would be my Tuesday workout, looking at it kind of visually on a number line. And again, lots of ways to think about it. But that's just one way to kind of go through and think about partitioning that number line in different ways. So again, area model or length models, we have lots of ways that we could choose to look at this, problems like this as we go through. And yeah, and that's what we just did. But basically, this problem as an equation would be half of 5/6, right? 1/2 times 5/6 will be the same as 5 twelfths. And again, when we look at it, even if we weren't sure if we could multiply across the fractions, we could see obviously that it works out that way that we do. Now, a good question here is when thinking of word problems and equations, to think of the meaning of the equations of each fraction is which of those fractions are of the same whole. All right, well, let's take a look here. So we want 1/2 of 5/6 of a mile. So in doing that, if we break this down, the 5/6 was of a mile on Monday, and we know our answer was 5 twelfths of a mile on Tuesday. But it's important to note that 1/2, right, does not mean half of a mile. That 1/2 is half of the 5/6, or half of that second fraction in the word problem. And this is always how fraction multiplication works. The first fraction is always of the second fraction, and the second and third are always of the same whole. This is different than we saw in addition and subtraction, where each fraction had to be of the same whole, but in multiplication we see the first one is not. The first fraction is of the second fraction. This is just looking at how the meanings work with multiplying fractions. Well, in doing that, obviously some problems, if we want to look at some visuals for it, it can be helpful to have a little bit more of a standard way of going about it. And one method that became popular with the connected math project curriculum a while ago was often deemed the brownie pan method. Well, it doesn't have to be used with brownies. But here's a situation. Let's suppose Adam came home from school and there was 1/3 of a brownie pan left over. He was hungry and ate 1/2 of those leftovers. How much of the whole brownie pan did he eat? Okay, well again, we can do this different ways, but let's look at this using a visual and kind of a standard way that some curricula presents and you may be familiar with going through here. So Adam came home, and this one builds on usually a square or rectangle model to begin with because it's easy to partition. And there was 1/3 of a brownie pan left in the fridge. So let's go ahead and shade those in. Got some lemon frosted brownies, I guess. But that's what was left. And it said that Adam came in and he ate 1/2 of those leftovers. Okay. Well, if I ate half the leftovers, you can kind of imagine it. That would be like me eating that piece right there, right? And if I want, I could even, if I want to draw a way across, that's fine too. It just helps imagine that if the whole pan was there, what it would look like. But basically, we can see that for breakfast, of the whole pan, I would have had 1 out of those 6 equal pieces, right? And that's what we get here. We just saw that we started with 1/3 of a pan left over. I ate half of the 1/3, and the visual would show us that in the end, I had 1/6 of the whole pan. Again, going back to our meanings, going back to our meanings we were looking at there when we word that, let's take a look. Now, wording these problems is actually very important because if we change the wording, it may not be a fraction multiplication problem directly anymore. So for example, here's that same problem, but what's wrong with this wording? There's 1/3 of a pan of brownies left. Kobe eats half of it. How many brownies did he eat? I mean, that's a valid question, but not for the multiplication question listed on your screen, because maybe he just had 1 brownie, right? If you cut it up, there's 1 brownie. And so it's important to word it in a way that matches the meaning. And so because that answer has to be of the same whole, it's important that the final question says, how much of the whole brownie pan did he eat? And we need to word it carefully to make sure it matches. And so again, here we see on the screen that the second fraction and the answer are both of a whole pan of brownies. But the first fraction, the 1/2, is just how much of the 1/3 that he actually had. So that's kind of how the meaning works there going through. So let's try a couple more, all right? So let's walk through one more, and then you can try one on your own to go through here. So in the first one, let's take a look at that. So first of all, if we were going to write a similar brownie problem for the first one, the leftovers, again, are always, you start with the second fraction, because that's the one that's of the whole pan of brownies by the meaning of multiplication. So we might say again, let's say that Anna came home from school and there was 4/5 of a brownie pan left and she ate 2/3 of that brownie pan. How much of the whole brownie pan did she eat? I mean, that would be a valid question. So let's take a look. Let's take a look again at just when we draw the visual of this method, what that would look like. So pulling that back up, we would start with the brownie pan. And coming home from school, there was 4/5. And you always want to start drawing it one way. Draw one more here. So it's into fifths. I'm going to shade that in just for some nice color. So that's what was left. And when she came home, she ate 2/3 of the 4/5. Now, again, in this little drawing type of algorithm, we always cut it the other way to take a look. So if she ate 2/3 of it, basically, she's going to eat 2 of those 3 rows. In some curricula, they have students kind of shade in that other color to go through. You know, there's different ways to go about it. But we see that 2/3 of the yellow amount would be the one that's overlapping right here. And that area there where they're overlapped represents, 2/3 of the brownies that were left. And how much is that? Well, we see that that would be kind of 8 pieces. Out of the whole pan, there would have been 15 pieces in the whole pan of that size. And so again, the visual here just helps us see that she would have eaten 8/15 of the pan total when she came home. And again, after looking at this, students can make quick connections, just realizing again that multiplication of fractions is nice. It just multiplies right across, and we get the same answer with just seeing the algorithm in action there. It's a nice simple algorithm to take a look at. All right, so for you, why don't you take a moment and why don't you try the second one? Why don't you try and pause the video and draw out the second one and see if you can get a good word problem and a good visual to go along with that one, okay? All right, so let's take a look at a couple others real quick because, as you go through standards, it goes from just, a fraction kind of less than 1 by a fraction less than 1 to dealing with mixed numbers as well. So maybe we can take a look at a couple of these. Again, I encourage you to pause the video and play with these for a second and think, what are some ways that you might actually draw these out or make sense of it in some different ways. So let's go ahead and do that here and take a look. So that first one, we have 1/2 times 2 3/4. So let me go ahead and pull up the document camera here. And, if we were looking at that, we might say, if we wanted a word problem, I suggest starting with the second fraction. And maybe Kirsten had 2 3/4 pounds of tofu. I love tofu. And let's say she gave half of that to Becky. And we're wondering then, well, how much did she give to Becky? So that would just be, half of 2 3/4. So again, as visual, we can do this lots of ways. As an area model, first we need to define here a pound of tofu. So let's say that's our pound of tofu. So in the beginning, let's draw out what Kirsten started with. She had 2 3/4 pounds of tofu. In doing this, I recommend that when you cut something into fourths, again, just like the last model, just draw it in one direction. We'll see why in a second. It makes it easier to partition. But that's the starting tofu. And Becky, she gave Becky half of it. Well, here's a nice thing. If you want to partition in half, what we could do is just kind of, again, just like the other model, it's really the same thing. We're just coming the other direction. And if I come the other direction and cut it into 2 equal parts, we can imagine that Becky would just get, again, maybe the top part, the half that would be on top here, and that would represent the half she would get. Well, how much is that? Well, again, we could think of it a couple ways. One, we could just think of, well, these two together would give Becky a pound of tofu. And then these 3 pink pieces here would be 3 out of the eighths of the next one. And so we should get that she gets 1 3/8 pounds. And that'd be the same. Some people, when they do this, like to say, well, let's get them all to be the same size pieces. So since these were in eighths, we could apply those same cuts over here. And again, since each of these little squares are eighths, we might say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We could also say that she also got 11/8, looking at it that way, but we know you could make 1 full pound out of that with 3/8 left, and of course we get the same answer either way. And again, if we take a look at more of just an algorithm, there's different ways to do this, but one common way is to just know it's often helpful to turn it back into a fraction greater than 1 here. So if we had 2 wholes broken into fourths, that would be 8/4. Adding 3 more would be 11. And so that'd be 11/4. And again, just using the algorithm here, we can multiply across and, see again that we definitely get the same answer. So that's 1 for that one. The second problem we were looking at on the screen was a mixed fraction by a mixed fraction. And I believe the one on the screen was 1 1/4 times 1 2/3. So again, I encourage you to pause the video for a second and just play with it. What do you think visual for this might look like? How could you draw it out to make sense of it? Give it a shot. All right, well first, let's see if we can think of a quick word problem here. And again, when multiplying, I suggest always starting with that second fraction. This is going to be of the whole. And let's say this time we're going to do, a pound of pinto beans. I'll explain here. So let's say that we're going to make a batch of chili, all right? And 1 batch of chili takes 1 2/3 pounds of pinto beans. And I have some guests coming over. I need a little more than 1 batch of chili, but I don't want to overdo it. So I'm going to make 1 1/4 batches of chili, all right? So I'm going to say that again. So each batch takes 1 2/3 pounds of pinto beans. And I want to make 1 1/4 batches. How many pounds of pinto beans will I need? Just, lots of problems. There's one. We're dealing with some chili here. So let's think of drawing this out. Well, to start, let's think 1 whole batch. Well, let's think here. Let's start with defining our whole. So let's let the whole be 1 pound of pinto beans, because that's the question. How many pounds of pinto beans do we need? So there's 1. And for the first batch, it says I would need 1 pound of pinto beans and 2/3 of another pound, and that would give me, 1 batch of chili. But I know that I wanted a little more than a batch, but not too much more, so I decided that I wanted also to have another quarter batch. Well, let's think about it like this for a second. Let's go through, and I'm going to draw this out the same way, and start with a whole batch would look like this, right? If I needed the whole thing, but I don't, that would be a whole batch. But I only need 1/4 of that. So like last time, what we can do is just use that same type of principle of cross-cutting. If we break it into fourths, again, we only want 1/4 of it. So I can take one of those rows and realize again where that overlap is the amount we need. So now the question is how many pounds, all right, how many pounds of pinto beans do we need? Well, again, right now I have lots of different size pieces. So we could add this up in different ways, but one way is to go back and realize it's easier to add them up if we figure out the same size pieces here. And so just to clarify, I'm going to put in pink everything that we are going to use, just to clarify the pink from the yellow. So that was our first batch, and that was our quarter of a batch. So let's count this up. And it looks like our smallest piece down here was when we broke this into 12ths. So if we just, again, apply those cuts to other things, if we want, this is one way of thinking about it, we could apply those cuts to each thing. And again, now if we count the pink pieces, I have 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So I have 25, and each of those were eighths. So I have 25 of those eighths of what I would need. And how many pounds is that? Well, how many groups of 8 go into 25? 3, because that would make 24 pieces. And there'd still be 1 left over. And so, again, a visual there, just seeing it's possible with mixed numbers that we see it would take 3 1/8 pounds of beans to make that much chili. And looking at just an algorithm again, just to verify what we're doing here, one way of doing that is to go back to think about putting these back into fractions greater than 1. So in the first one, I could write the equivalent fraction of 5/4, and the second one, the equivalent fraction of 5/2. And again, if I multiply across, again, obviously we get the same answer as we should going through. But again, the goal is just seeing how the visual connects to the algorithm there and looking at that. All right, good. So that kind of wraps up some things with multiplying of fractions and looking at some progression of fractions through the standards and seeing some visuals and kind of how those visuals model with the algorithm. But let's take a look now at division of fractions. And again, let's start with a whole number divided by a fraction. So for this one, what does that mean to you? Maybe stop for a second and think about that. What's a word problem that would make sense for 4 divided by 1/3? What would be a visual you could draw that would actually show what 4 divided by 1/3 actually means? So before we do that, let's go back and just think of where we started here. Let me pull this up large screen here, sorry. So again, we're going to start with a word problem and maybe even some estimation. We'll talk about that. And then, again, like the progression before, we start purposefully with a whole number divided by a fraction so we can relate it to what we learned previously when dividing with whole numbers, starting back in 2nd and 3rd grade. So for example, when we had 8 divided by 2 earlier, we knew one way of thinking about that was, again, how many groups of 2 does it take to make 8? How many 2's go into 8? So if we see something like 6 divided by 1/2, when we can relate it back to previous meaning and connect that knowledge, that's helpful. How many 1/2s, how many groups of 1/2 does it take to make 6? How many 1/2s, go into 6? We can use that same type of groups of language again to go through that. And again, here with division of fractions, we see that in the core standards, they really come out in 5th grade, is now what we're talking about here. So let's go back to that original question, 4 divided into thirds. So here's maybe a situation. You have 4 doggy biscuits and you break each of those into thirds. How many pieces of biscuits do you have to give your dog? Well, again, let's think about it. Well, if we break it up, do you think we'll have more than 4 pieces, less than 4 pieces? More than 8 pieces, less than 8 pieces? More than 12 pieces, less? Just the kind of questions, again, could have us start thinking about the question. And can you go ahead and draw that up? What would that look like for you for a second? Yeah, so this one is, we could draw it lots of ways, but again, if this is a dog biscuit, and if I go through and have 4 of those, we broke them into thirds because, we got to make our dog work for these biscuits here. So if we break them into thirds, each one is broken into 3 equal pieces. And so here we can just see that, of course, well, there would be 12 pieces to give my dog. And we always want to connect that, back to the equation. So we had 4 doggy biscuits. We divided them into thirds each. And again, we see that the answer is 12. And just relating back to the connection between the visual and the original math equation is a good place to start. All right, so whole number divided by a fraction. So one for you to try again. I'm not going to draw this one out. Why don't you try this one out and pause the video and read that problem and draw that out. The answer should be 8, but see how, when you draw it out, what are some ways you might go about doing that one? It's a little different than the first one. So that last problem, let's think about the meaning there. So we had 3 yards of ribbon, and it took 3/8 of a yard to make an awesome bow tie. Thinking back to a couple units ago, when we think about the meaning of division there, we had the total amount was 3 yards. The size of each group, to make each bow tie was 3/8. We were trying to figure out how many bow ties we could make, or in this case, what number of groups could we make. And this goes back to the idea of measurement division, which was kind of like we said repeated subtraction. When you start with 3 and you see how many times you could subtract 3/8 until you have no more to subtract. So just connecting back to earlier learning, this is the model that works best with dividing fractions, a measurement division scenario. Works better than the partition division in general to comprehend and just make it easier to draw models for. Now, in thinking of that, when we think about, again, how fraction division works, it's a little different as well. Because in the meaning of those, the 3 stood for 3 yards of ribbon. And the 3/8 also stood for 3/8 of a yards of ribbon. That was how many yards per bow. And the answer, though, was not yards of ribbon. The answer told us the number of bows that we could make. So again, we see this is different than fraction multiplication and different than addition and subtraction. Just the structure of it works a little differently. The first 2 fractions are always of the same whole, and the last one represents the number of groups that we can make depending on the word problem. So again, the structure here is a little different and important to make note of that just as we word these to make sure they're worded correctly. So in our book, there's a nice little scenario here that I think is helpful to look at, which is nice. And if we take a look at it, here is a situation of a fraction divided by a fraction. The last one, it was a whole number divided by a fraction. So I like this way of thinking about a fraction divided by a fraction. We have a scenario here about serving size, and serving size can work well for these problems. Like in the first one, it says a serving is half a cookie. How many servings can I make from 2 cookies? Well, starting with that one, you might imagine we could, again, cut each of those cookies into halves, and there'd be 4 half cookies, so there'd be 4 serving sizes, right? And in number 2, how many serving sizes can you make from from 1 cookie? Again, similar thinking. I think we'd agree that you could make 2 servings if that's true. But then it changes with number 3. It says a serving is half cookie. How many servings can I make from 3/4 of a cookie? So starting with 3/4, how many servings would that be? Why don't you think about that for 1 second? And while you think about that, I'm going to pull up some virtual manipulatives here for us to look at. I'm going to use the polypad manipulatives here coming through. I'm going to pull up, they don't have the circles on this one. So let me find one that has the circle manipulatives for us here. Let me go to, a different one here. To this site here. I was on the wrong site. And this is the mathlearningcenter.org, and they have a nice fraction tab to look at that we can pull up here. Okay, there we go. And so let's take a look at this first one, and this is what we were starting with here. All right, so I'm going to bring this down, and we had 3/4 of a cookie. And let's say, again, we know the serving size is half of a cookie here. So when we look at it, let's take a look. So here is 1 serving here, and I'm going to pull up a second one here, and this would be a second serving, but we don't have that. We don't have that yet. So let me go back and start again. Sorry, it took a little bit to catch up. So here's what we started with, right? We had 3/4 of a cookie. A serving size is 1/2, so how many servings do we have? Well, definitely we have enough for one serving right there. And if we take a look, do we have enough for a second serving? No, we don't. We only have that one little piece there. But we can see that piece is half as much as we need for the second serving. Interesting. Well, that makes sense, right? So we see here that we started with 3/4. Oops, I'm going to grab this one. So we started with 3/4, and we were wondering, how many serving sizes could we make if those serving sizes were 1/2? How many 1/2s could we make? And we saw that up top we can make one full serving and 1/2 of a second serving. So that should be the correct answer, which it is. All right, so coming back here, let's take a look at the next one, number 4. It says the serving size is half cookie. How many servings can I make from 3/8 of a cookie? So looking at that picture for number 4, first of all, I encourage you to reason this out. Do we have more than a serving or less than a serving? And looking at it and thinking about it, I think we agree we have less than a serving. So the question is, how much less, what do we have then? Does that cookie represent half of a serving? What fraction of a serving is that? So let's go back to the manipulatives and see if we can draw this out here. Oops, let me go back to this one. Go back to our circles here and start over again. So this time we started with 3/8 of a cookie. Let's make it a green cookie this time. So that's where we started. And we know that the serving size, again, was half of a cookie. So there's a serving size. And again, I think we see that we have definitely less than a serving here. The green is less than the yellow. But if that serving size is one serving size, then how much do we have? Well, let's just put it over there and take a look. Well, if we look at it like this, to make a full serving, I would need 4 of these pieces. 4 of these eighths would make a serving, but I only have 3. I have 3 out of the 4 pieces I would need to make a serving. So thus, the green part represents 3/4 of a serving. And again, let's take a look. What we said here is we started with, oops, let me get back to my drawing tool here. We started with 3/8, 3/8 of a cookie, and we wanted to see how many 1/2s go into it. And we knew it was less than 1, and by looking at the visual, we saw that the answer should be 3/4 of a serving. That's all we have. Less than a serving, it was 3/4 of a serving. Now, something interesting here, if you notice the pattern here? If I divide the numerators, 3 divided by 1 is 3, and 8 divided by 2 is 4. Well, that's interesting. I just divided across, and I got the right answer. Think that always works, or would we get lucky here? We'll come back to that in a moment here. All right, well, back to the PowerPoint. We look at the PowerPoint here. The last one I'll leave for you to try and draw out. All right, a serving size is half a cookie. How many servings can I make from 5/8 of a cookie? So again, is that more than a serving? Less than a serving? Looks like more than a serving. See if you can reason it. Give a second. See if you can draw it out or think about it. I'll give the answer in just a second. The answer for that one, if we did a similar model, would be 5/8 of a cookie would represent 1 full serving and 1/4 of the second serving if we went through. That would be the correct answer there. And again, in this one, if we look at the standards, really we're dealing at a 6th grade standard here. Interpret and compute quotients of fractions and solve word problems involving division of fractions by fractions by using visual fraction models and equations to represent the problem. So that's exactly what we were just doing. So, as we build models here and take a look at it, with these, there's lots of models to go through. And so let's just do a couple here quick together. And encourage you to draw these out and think about them and pause the video again as we go through. So let's start with this. Let's suppose again that we have 1/2 divided by 1/8. And we're going to do these fairly quick here as we run through. But let's take a look at 1/2 divided by 1/8. I'm going to bring up this time those tiles here. And again, let's say that we have a 1/2 pound of sugar, and we are baking muffins, and each muffin is going to take, oops, I'm sorry, I think the problem originally, let me go back for a second. The original problem was 1/2 divided by 1/8. Thank you, 1/2 divided by 1/8. So let me go back to the here. So I'm going to draw that out just so we have make that connection here. So we're looking at 1/2 divided by 1/8. So again, thinking about the language, is how many 1/8 does it take to make 1/2? Oops, so if I go back to my arrow here, so there's our 1/2 pound of sugar. Each muffin, these are big muffins, takes 1/8 of a pound of sugar. How many muffins can I make? Well, how many groups of 1/8 go in? Well, let's take a look. Again, using a model, we can just see how many 1/8 go into 1/2. And again, we see that it should be an answer of 4. Yeah, so that would be it. If we take 1/2 divided by 1/8, the answer would be 4. And that's just a model for the first one there. So let's take a look at another one. If we take a look at, how about something like this? 3/8 divided by 1/4. All right, so let's take a look at that one. So 3/8 divided by 1/4. Let's start a new pad here. And I've got 3/8 divided by 1/4. So let's go back again. Let's just use the same analogy here. That it says I started with 3/8 of a pound. I started with 3/8 of a pound of sugar. So let's go back and let's build those out again. So here are 3/8 of a pound of sugar. This time, let's make a loaf of banana bread, and each loaf of banana bread takes 1/4 of a pound of sugar. So here is a fourth. Do I have enough to make one full loaf? I do for sure. Do I have enough to make a second loaf? No, I don't. So the question is, I can make one full loaf, but how much of a second loaf can I make? Well, looking at it this way, I only have this 1 out of 2 pieces I would need to make a second batch. So I can make one full loaf right here, and this represents half of the next loaf. So the answer here would be that I could make, again, 1.5 loaves of banana bread, as the visual shows there. Interesting, if I divide across here, I would get 3/2, which is 3/2, which is the same as 1 1/2. So again, interesting, we see that dividing across gets us the right answer again. All right, let's do one more here, and take a look at let's take a look at this one here for a second. So here's 1 divided by 2/3, and let's think about this one for a second. All right, so I'll draw that up here. We have 1 divided by 2/3. How many groups of 2/3 can fit into 1? So let's say, again, maybe I have one large, I don't know, a candy bar here. And let's say a serving size, oddly enough, is 2/3 of a candy bar. So how many servings would represent if I ate this whole thing? Well, all right, well, let's take a look. First of all, do you think it's more than a serving? Yeah, it definitely looks like it. More than 2 servings? No. So let's go through and take a look. So 1 serving would be 2/3 of the candy bar. So right there, that would represent, again, 1 whole serving. Right there. Oops, 1 serving. And this part of the candy bar left is not enough for another whole serving, but let's take a look at how much it is. And visually, we might choose to kind of take a look out and realize that a second serving would look like that. Don't have enough for a whole thing there. But of that second serving, I have half of what I would need for the second serving. So this piece here, it is 1/3 of a candy bar, but the answer is in terms of servings, that would represent 1/2 of what I would need for a serving, right? And so the answer to this question should be 1 1/2 servings. And it is as we go through. So again, just looking at models like that, we just see that, instead of just teaching a rule, using some concepts and some visuals, we can see why the answer makes sense, and then try and develop some other, algorithms and some efficient ways to get there. So I think that's where we're going to head next. Let's take a look at some algorithms along with that. And so for you, tell you what, if I asked you to solve 3/4 divided by 4/5, what would be your go-to method? Take a second and do that, just with any algorithm you would do. Pause the video, solve it out. Okay. Well, again, there's two main algorithms. There's more than that, but there's two main ones that we see in schools and curriculums here. One is called the common denominator method, and the other, which is kind of more one I bet you probably did, it's as far as what has been taught when you were in school, was the reciprocal or invert and multiply method. So let's unpack these two algorithms quickly here. So in order to do the common denominator method, let's go back to that question we saw earlier. With fractions, can you just divide across? Like in the first one, if we just divide across, we'd get 3 in the numerator and 2 in the denominator. Is the answer 3/2? It is. Put it in a calculator, invert and multiply, you will see you get the same thing if you divide across. For the second one, if we divide across, we get 4/3. That's the right answer. If you use any method you want, you will get the answer of 4/3. So interesting, so why isn't the algorithm, why don't we, I mean, if this is true, why are we often taught to flip and multiply when we can just divide across? Well, and the answer is true, we can divide across, but like these examples here, it ends up that all the numbers are factors of each other, so they divide nicely. You can imagine if I put some unfriendly numbers in there and we tried to divide across and they don't divide nicely, you don't really get much further than you did. So that's why it's not taught standardly, but it's good to know. And remember, that's fine. Just like you multiply across, division is related to multiplication. We can just divide across and get the same answer. And with that, that's why one method that's taught in schools is the common denominator method. It uses that principle to go through. So let's take a look at these two together. I have 3/5 divided by 2/3, and then we're going to look at 7/8 divided by 5/6. All right, so let's look at the common denominator method for a second here. I'm going to go back to the .cam. The nice thing with this method is it builds on what was taught earlier with addition and subtraction. Just that common denominators is a skill they've already learned and something that makes sense if we're trying to divide. Maybe it's helpful if we divide the same size pieces, just like before. So to do that, we might realize again that a number that these both could go into nicely might be 15. So to get a common denominator, we might multiply by our giant 1 on this side by 3/3, on this side by 5/5. And again, remembering that multiplying by 1 doesn't change anything. So we know that 9/15 must be the same value as 3/5, they're equivalent. And over here, we get 10/15 is equivalent to 2/3. Now that you have a common denominator, and knowing that we can just divide across, let's see what happens. Well, the first thing that happens is in the denominator, you always get 1 every time because we're dividing the same number by the same number. In the numerator, well, it's not nice, but that's okay. Watch what happens. We just get 9 divided by 10, or 9/10. But every time, because we have 1 in the denominator, the answer will always be just whatever the numerators divided are. And that's just a nice algorithm going through. The answer is 9/10. And if if this is new to you, we could look at the invert and multiply method just to show if I flipped the second one and got 3/2 and multiply across, I get the same thing. So this was common denominator, and this was kind of multiplied by the reciprocal, and we get the same answer. Now again, I agree, the top one took an extra step, getting the common denominator here, but it also doesn't rely on kind of a magical rule that we see in the second one. It makes a little more building on some sense making with our knowledge of operations. But let's take a look at the second one. I want you to pause the video for a second if this is new to you and solve the second one using the common denominator method. Okay, so pause for a second and then we'll just see if we get the same thing. So for this one, first of all, to get a common denominator, we might have chosen 48, which would be fine. You don't have to use the lowest common one. The lowest common one would have been 24, so I'm going to do that, but it's not necessary. Again, multiplying by a giant 1, I'm going to multiply this side by 4/4. And to get to 24 on this side, I might multiply by 3/3. So what that might look like is an equivalent fraction would be 21/24. And on this side, we'd get 20/24. And if I just divide across, the answer is going to be 21 divided by 20. And at some point, teach students just write that down, but just to show all the steps, I'm going to show that our denominator was 1 and our numerator was 21/20 going across. So, and that could be written as 1 and 1/20. So that was our common denominator method. If we use the invert and multiply method, let's just take a look at that, or multiply by the reciprocal method. We should get the same thing, right? We multiply by the second one, by the reciprocal of the second one, and I get 42 over 40. If we simplify that, dividing each by 2, I get 21 over 20, which of course is the same thing we had above. And again, we see some pros and cons. Multiply by reciprocal seems to take less steps in general. But again, there's this notion of why. I thought we were dividing. Why are we multiplying? Why would we flip the second fraction? Like, what's going on? And the first one, we're building on some common prior knowledge of getting common denominators and knowing that multiplication and division we can divide across. We can go through and get that answer. So let's unpack the why of this for a second. Multiply by the reciprocal. Why does this actually work here? So let's unpack this second one and take a look at why this multiplying by the reciprocal is a thing and why this works. So let's start. We have 7/8 divided by 6/5. And in math, basically, when there's a shortcut like multiply by the reciprocal, it's always a shortcut for something. The question is, what is it a shortcut of? So if we want to see that, here's one way to think about it. I'm going to rewrite it a little different, just for the sake of this example. I think we'd agree that I could rewrite this division problem in terms of this. It's still 7/8 divided by 6/5. Why is this problem messy? Well, it's because we're dividing by a fraction. So wouldn't it be nice if we could divide by something more friendly? I mean, what is the nicest thing to divide by? The thing that gives us no problems? Yeah, 1. If we could divide by the number 1, that is the best thing to divide by. So what would we have to do to change this to a 1? Well, one thing we could do is we could multiply it by 6/5. Oh, I'm sorry, by 5/6. Oh, you know what? I changed the original problem by mistake. It was here. So I'm gonna go back to just use this as our example here, but I think I reversed this from the original one, but it's okay. But so the reciprocal of 6/5 would be 5/6. Sorry about that. But I can't just do that, right? That changes the value. Unless the only thing we could do is multiply by a giant 1, right? When we multiply by a giant 1, it doesn't change the value. So this is a very creative giant 1, 5/6 over 5/6. That's a valid move. We're just multiplying by 1. And again, in the denominator, 6/5 times 5/6 would be 30 over 30, which is just 1. Well, that's nice. In the numerator, I'm just going to, just for now, leave it unsimplified and just write it like that. Just saying what we'd multiply out. And again, anything divided by 1 is itself. I get 7/8 divided by 5/6. And so what we see, I'm sorry. Sorry, going a little faster. So when we multiplied by the reciprocal, we multiplied by 5/6. And so in the end, we see this would be the same answer as the original problem because we've done nothing to change the actual answer. So by skipping that step, we went from a division problem to a multiplication problem where we multiplied by the reciprocal. And that's one way of seeing why that works there going through. All right, well, coming near the end here. So I guess the question is, so what do we know about this? What methods do we see in curricula and what's the deal? Well, this again, there's no right or wrong here, but I think our author would argue, and does argue in our text, that the common denominator method can be used a little more meaningfully by children who understand equivalent fractions and a measure out meaning of division and relating to prior knowledge. So sometimes that one is the one that can be a little more able to make sense of as far as what's going on and why that works. Ideally, although I know it doesn't always happen, the reciprocal method, methods like that are kind of based on a trick, definitely are helpful, they're efficient, but typically are used after students are ready to understand why it works. Yeah, it's one of the goals in math is not just to teach tricks, but to teach math. And so if we can't justify why a certain shortcut works, sometimes we'd argue it's not the best time to introduce that yet. So just a thought on that, and you have to make up your own decision on that one. So thank you for sticking with me. This was a longer video today, but in the end, let's go back. And what we see again is just the importance of making sense of things, reasoning and sense making, using contextual story problems, using benchmark estimation, try and use a lot of visuals and models, making sense of those models and how they connect to algorithms, and attacking some of those misconceptions explicitly. So hopefully this gave you a little new insight into some of the nitty-gritty behind multiplying and dividing fractions. And until next time, have a good one.